It's human nature to stretch, to go, to see, to understand. Exploration is not a choice, really. It's an imperative.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts in England and Sweden, Matthew, Rosalind, and Boldt-Christmas.
Oh no, I almost feel bad. Just before we came to air, I discovered that poor old Michael Collins, literally my favourite astronaut as well, has passed away.
I know. I saw. It's so sad.
Age 90, so he did have a pretty good innings. And it has to be said, if you've been to the moon, that's quite a good achievement, isn't it, in life?
Where else do you go?
Where do you go after that? Yeah.
Yeah. It's really, really sad. I mean, he's joining his colleagues.
Buzz is the only one that remains then, isn't he, from that trio?
He certainly is, yeah.
Weird thing, he was born in Italy.
Really?
But yeah, so Michael Collins was born in Italy, in Rome, in 1930. So
Michele Collino.
Yeah, exactly. She's actually called Michelle. No, I think his parents were obviously American on some military base, probably in Rome, I would have thought, or something like that.
Presumably so.
So I would think he's one of the only non-American born to go to the moon.
Right? That's a good point. I hadn't thought of that. I don't have the birth certificates of the others on hand. I can't think of it.
But I wonder how many Italians know that Michael Collins was Italian or born in Italy.
I mean, Michael Collins does not strike me as a very Italian name, I must admit.
No. Well, he definitely wasn't.
Maybe more Phil Collins? Yeah.
Phil Collins.
His long lost.
Is definitely not born in Italy. Oh, actually, I don't know.
No.
I think he was born in London somewhere, though.
Yeah. But I mean, yeah, surrounded by his family, aged 90. Truly, if you have to choose, right? That's the way.
That is the way, yeah. I mean, we did on podcast 142, he was Astronaut of the Week. And when I got to the end of the summary, this is what I said. In summary, Collins is a brave, bang-out pilot, professional beyond belief, modest and a sensitive family guy. What a freaking legend. I think that pretty much sums him up. I think that was Michael Collins.
Could not have said it better.
And he definitely wrote the best book about Apollo as well.
Did he?
Yeah.
I haven't read any of them, actually. Do you have any suggestions?
Yeah, his.
If I'm going to read one book...
If you're going to read one book, yeah, it's Michael Collins called, what is it, Holding the Flame or something like that. Something about a flame.
I'll take it.
Yeah, it is, honestly, it's the best book about Apollo.
Yeah.
It's brilliant. It's really, really, really cool. So, yeah, it's probably a good time to read it.
Yeah. Moment of silence, Michael Collins.
Moment of silence. So what are we talking about this week, Lynn?
Today, we are talking about exoplanets, the best topic, yes. And in particular, exoplanet detection, because they are so freaking sneaky, it is hard to find those, I was going to say bastards. Can I say bastards?
You can say
buggers. I don't know.
Buggers. Those little buggers hiding in the light of their stars. Yeah. That's what they're doing.
That is the technical term. I am awaiting the decisions of the International Astronautical Union to see if they agree on the new terminology.
The exoplanets.
Still pending.
The little buggers.
Yeah. Those little
buggers. So,
hey, that could be a good thesis title.
Yeah, exoplanets, those little buggers. Yeah, so we talked about exoplanets the first time you were on, but I thought I've got an interview with Alok Jha, who is the Economist's science correspondent. And we had a little chat about exoplanets. So I thought it'd be a nice time to pop that one in here. So stay tuned for that because it's really interesting. And I was quite pleased with my ice cream analogy that you'll hear.
Oh no, yeah. I'm definitely listening.
Yeah. So it's yes, you'll have to check it out. But exoplanet direct. I want to talk about direct detection because I think when I've talked about it before. We've always talked about the sort of two main methods, which are...
The two most common methods are radial velocity method, which is the wobbly method, which is when you're looking at the central host star. It's when the planet that's going around the star very gently tugs on the central star because, of course, planets are much smaller but they're usually than their central host stars, but they do still have a gravitational pull, so they do still affect their host star. So that also means that bigger planets or, planets with a greater gravitational pull affect their host stars more so. So that method is very good for detecting, near-in big planets.
It's actually quite a big effect, isn't it? Because Jupiter pulls the sun completely out of the size of the sun. So in other words, they're actually like a binary system. They're actually orbiting each other.
Yeah.
It's just that Jupiter orbits the sun a little bit more than the sun orbits Jupiter. But yeah, it's pushing it.
Exactly.
It's pushing it around. But I always think it's insane that Doppler effect that you get from that as it sort of pushes and pulls it. You can see the color change. I still think that that's ridiculous.
It's gorgeous. I guess I'm trying to think of a way to explain it with words only. Something that would only really work for a British audience. But the maypole wrapping when like the kids are running around the pole and they're tying the ribbons around it. That's kind of the best analogy. You can imagine how the maypole does wobble because there's all these pulling happening on it. And in the same way, the central star, the host star, does get tugged, but of course the size of the planets makes a difference. How many planets there are, there's a lot of different influences on how it wobbles, how much it wobbles, when it wobbles, and all this stuff. So
I've got a question for you. Can you do an impression of an ambulance coming towards you, passing you, and then going away? It's okay. It's okay.
It's fine.
It's good.
I
think it demonstrates.
On it.
Yeah, that's a good example of the Doppler effect, right?
Maybe it's more like a high pitch, more like
Yeah.
that would be a really fast ambulance.
There we go.
There's something going on there.
Yeah, and that's how it works, right? So as the star comes towards you,
higher in frequency
as it comes towards you,
which would make it more blue. If you're picturing the rainbow, I hate to tell you guys, but there is a correct way to visualize the rainbow, which is obviously starting with blue and then going to red. None of this red to blue business, please. And so as the pitch of the pitch,
it's the pitch of the color frequency, but it's the same phenomena, isn't it? It's the same phenomena.
I always, especially when I talk to like in outreach capacities, actually with kids, what I do is I tell them, okay, you know how in sound there are some sounds that we can't hear, like a dog whistle is too high for the human ears to hear, or how whales speak in like a really low tone that we can't hear. That's because there are sounds that the human ear is able to hear, and some of them are too high or too low, so we just can't access them. And then I tell them, this is where I blow their minds, that light has the same deal. Our eyes can cope with red to blue, but there is also beyond, above and below. And so when we say blue shifted, we don't literally mean that it turns blue, because we're usually talking about ranges outside of the optical spectrum, but it's towards that end.
But it actually does get bluer and redder, right?
Yeah.
So it's actually getting...
Yeah, no, it actually is as well. It's because the emission spectrum of stars is pretty wide. It's not just like one wavelength. They cover like a sort of black body curve, if you will. So it's just that the whole thing moves towards the blue and or towards the red. It's just a good way of visualizing. You could equally have said it's moving towards the X-ray or towards the radio waves, because it's still a direction.
Yeah. Well, I just think it's incredible that the star's actually not moving very fast. It's only a few meters per second, isn't it? Yet you can actually tell that color shift. I mean, it is actually ridiculous. So that's the radial velocity method.
Or the Doppler method, yeah. The other one is the transit method, and this is my favorite because it's the one that I work with. And that's the one where if you imagine a distant star, like a big fat lamp hanging in your face, and then the planets that go around the star they're orbiting around it, and then as they pass in front of the face of the star, then you can imagine that blocks it out. It's like a solar eclipse. When something is moving in front of the face of the star, then the light gets blocked out, right? And so that event is called the transit. So when planets transit in this manner, they do block out some light from the host star. Can be a lot, can be a little, depending on how big the planet is in comparison to the diameter of the star's face. But however much light is being blocked out, there's still that dip there's still some amount of light that gets blocked out. And what you do is you see a dip in the amount of light that's being received. So if you're seeing light, and then comes this little bugger exoplanet in front of the face again, then that blocks out some light. So then it goes light, less light. And then while the planet is in front of it, it's going less light, and then the planet goes away past the phase, and then you go back to the amount of light you were receiving before. So when you look at the amount of light received over time, you do see this dip, as we call it. And when you start to recognize this dip in the so-called light curve, you can identify, hey, that must be a planet. Loads of asterisks there, but yeah, that's the basic idea.
Yeah, I mean, presumably it gets complicated when there's more than one planet. But...
And there's a bunch of things. There's and it's even something like, what if there's a solar flare, or a solar spot? Then you suddenly have a dip in the amount of light.
You have to do a lot of observation and understand how the star works. Almost like you're taking it away, aren't you? Taking away all that stuff, the noise. And
you have to model the surface of the stars. And I mean, more importantly, the planets are very small compared to the star. Yep. So it's really tricky just to detect. Like, if you had a big, fat stage light in your face, and a little mosquito went in front of it, would you notice it? Maybe not. So
well,
we're talking about
even more ridiculous.
Very small amounts.
Even more ridiculous is both those methods, as far as I can see. Although I should imagine the transit method is even worse. Is you only see these planets if you're in the right plane of looking at the star, right? So I mean, so if they're even slightly off, you're not even going to see them. If the plane's even slightly off. And I guess the same with the radial velocity method as well. If it's pulling it up and down, you're not really going to see it.
Exactly. If you're like above it, so to speak. For the transit method as well, there's something you have to bear in mind, which is that you get something called limb darkening around the edge of a star, where the faces of the stars that we look at, they're not like a perfect 2D yellow circle. There's effects at the edges of it that makes these models trickier as well. So lots of ways to do it. This is why we're working very hard, and we're getting better telescopes, better ways to deal with the data we get from the telescopes, all of this to improve our understanding and abilities.
Did you get your arms sunburnt when you went out on your walk today? Because that would be like limb darkening. Hey! What a dinge. So there's 4 other methods that I thought were really, really cool that don't get talked about much. And that's the one's called the reflection and emission modulation.
I've heard of it. I'm gonna politely add here that this is no longer my field of expertise.
It's pretty cool. If you've got planets with high albedo, they will be reflecting light. And as they go round, you see the phases of those planets. Just like when we look at something like Venus or the Moon, they have phases, right? Because they're within our orbit of the Sun. So these planets going round the star will also have phases. So as they go round, the whole system will go brighter and darker with the way that they go round and go through these phases. And so that's actually another way of detecting exoplanets, and it's been done. So it has actually been done. There was 51 Pegasus B was the first exoplanet discovered using that method round a sun-like star.
That's really cool. I actually hadn't heard of that. I don't do that much detection per se. So
and the other one that I really like is this thing called relativistic beaming. So, which is really cool. This is the one where I was trying to think of how to describe a planet as it tugs on the star. Is a bit like know when you pull a baby's cheek, when you can't resist squeezing a baby's cheek. It's like that. Like as a planet goes round, obviously the star will bulge. Who's a good like that. As the planet goes round, obviously it's making that bit of the star bulge a little bit, and therefore that bit of the star will actually be denser. Well, the matter of the star is being pulled in, and so it'll actually be slightly brighter. And so you can so it will kind of beam a little bit like a really rubbish pulsar. It will have this slight
the worst.
It'll be the worst pulsar.
It's trying.
You'd be able to just about see this effect. And again, they have discovered exoplanets using that effect in 2013. Kepler 76b, was the first.
Just mental.
That is mental, isn't it? The other one, the very first ever exoplanets discovered, was using pulsar timing.
Yes, I do know that one.
And that is super cool.
That is super cool. I just love pulsars in general as well.
Yeah. The reason why astronomers, I'm assuming, love pulsars, well, why everyone should love pulsars, is because they're these really useful clocks in the sky.
Yes.
As in you can do so many things because the timing of them is so precise that you can therefore use them to sort out loads of different stuff. And one of these things is sort out.
They can do your taxes.
Do your taxes.
They'll babysit.
Well, you might even be able to use them for interstellar GPS.
Yes, actually, that would be handy.
Yeah, so they are quite handy. And this one, if they've got, obviously, if pulsars have got planets going around, then they will wobble. But if they're wobbling around, then you'll be able to tell how their timing is being affected by this wobble. Yeah. And so, therefore, you should be able to pick out planets from that. And in fact, you can do that really easily, although there aren't many pulsars. So the very first exoplanet ever discovered, 1992, was round a pulsar. But weirdly, those two, Alexander Vershczan and Dale Frail, didn't win the Nobel Prize for exoplanet discoveries.
Dale Frail should have won a prize just for having a name that rhymes. I love
Dale Frail.
Dale Frail.
So he didn't get the Nobel. They didn't get the Nobel Prize.
I wonder why.
Well, I think it's because planets round pulsars are useless.
Incredibly useless. As in, like, that's like, is it really a planet or is it just a garbage big moon?
Yeah, it's garbage, and there definitely ain't going to be any life on it when you're that close to a pulsar.
It's a big asteroid.
Yeah. So, but also, I guess it's rare as well. It's not going to, discovering exoplanets using the other methods are going to find many more. That's a valid point. And for sure. And, so that's.
And more interesting planets that have like some semblance of chemistry left.
And here's the final of the non-direct methods, and that's gravitational microlensing.
Yes, love microlensing.
Yeah, I think I always think that would be really cool to use the sun to fly a spacecraft out to the point where the sun microlenses.
Yeah, that would be cool.
It's a long way out though. I think it's
and then at that point you're like, oh wait, that's where I left all my loved ones. What am I doing here?
Well, I don't think you'd fly a human out that far, because I think it's even further out than New Horizons has gone. Like it's
it must be.
It's hundreds of AU out. But yeah, you can use gravitational microlensing. So if a star goes in front of another star, it might just be, as it does it, that it will lens what's around that star, and so you can pick out the odd exoplanet. But what I find very annoying about that one is it happens once, and then it will never like the chances of a star going in front of the other star again is like really remote.
If you blink, you miss it.
If you blink, you miss it. And if you find them, it's like it's pretty hard to go back and check that what you saw was correct.
Yeah. Sorry, can we just get a quick second reading, actually?
No, you can't.
No. No.
But W First, I think, is going to go out there and do that type of
Roman.
Yeah, that's right. Yeah,
Nancy
the
Roman,
Nancy Roman, yes, as it's now called. Yeah, they're the kind of different methods that are normally used. But so, what do you know about direct detections, Linn?
That it's really hard, really, really, really hard to do. The problem with direct versus indirect detections, and this is actually something that's kind of in physics in general. This also applies to like how do we detect the presence of, a subatomic particle when we're looking at the Higgs boson and stuff like that. Let's say you are investigating the hypothesis of the existence of a mouse in your kitchen, right? And you have some pretty big, good theoretical grounds upon which to deduce this experiment. And maybe you have had some observations, like you have been hearing some squeaking suspiciously in your kitchen, and you have found that some food has been eaten. Now, these, though, are not direct detections of a mouse, right? They are indirect detection in the sense that only a real direct detection would be, I have seen the mouse in my kitchen, we are making eye contact. And it begs the question of when does many indirect detections become a direct detection. Sure, you could say that the identity of what is in your kitchen can only be confirmed when you do the direct detection, because maybe if you hear a squeaking, it's your floorboard, and maybe if food's gone missing, you have a small hungry child in your house or something like this. But a lot of science is built on, we say that we have proof or detection of this thing because we have triangulated it kind of with a bunch of indirect detections coupled with very good theory.
But I guess with the mouse analogy, what would be turning something from being a hypothesis into a theory, for example, would be mouse droppings, as in because
and you sample,
because you can't, because nothing else could create them.
But it could be a rat, you know. It could be something very similar. So this is where, and you kind of err on epistemology. You kind of err on epistemology, like what is a mouse? How do we know that anything is real? But
well, are we brains in a vat? Let's because
exactly.
Do we have to bring? So our brains being in a vat are part of exoplanet detection.
Yes.
So every time you discover an exoplanet, someone turns around and says, "Of course, this could all be a simulation."
Yeah, gotta check the brain in the vat before we publish anything.
Yeah, before we publish anything, we've got to check that we're not in a simulation.
Yeah, I guess in the exoplanet detection analogy, it would be like catching the mouse on camera, CCTV, busted, jail, everything. So the direct detection, I mean, in a field like observational astronomy, it's pretty easy to visualize what a direct detection looks like. It's us catching it. We can make it out with the equipment that we're using to detect it. Because here someone could snarkily remark that a direct, unless you land on the planet, do you really know it's there? And it's like, come on, yeah. I think direct detection. Here we're talking about like actually getting the direct observational measure.
Actually, literally photographing the object, right?
Exactly.
Not necessarily invisible light, though. It turns out.
No, almost never.
Almost never.
No.
But like, an infrared photo, like you said, is pretty much the same as a.
Yeah, and infrared is that's heat goggles, like James Bond night vision goggles kind of thing. That's relatable. Like if you saw a picture taken with an infrared camera, it would still make sense to you. It would basically be like iMac heat map filter on photo booth looking thing.
Well, weirdly, your mobile phone can actually pick up infrared. It's quite. Here's a little tip for you. If your remote control for your telly, you're not sure whether it's working or not. If you get the camera from your mobile phone and press it into the camera of your mobile phone, you can actually see the light on the screen.
I love that.
Yeah,
I love that so much.
So yeah, that's how I used to check with a. When I was doing electronics, I could check all my little infrared things that I was using.
That's so great.
But
it's my favorite thing about. I used to use. We had an infrared camera that we used to take around to schools for like outreach type stuff, and my two favorite things to show them was pouring a cup of tea or coffee into like a sealed thermos. Am I pronouncing that correctly?
Yeah.
Thermos.
Thermos.
Sorry, my Swedish accent is coming out.
It'll turn out that thermos was Swedish or something like that.
Greek, maybe. If you pour a hot beverage into something like a cup of tea, or if you pour it into a mug or like a thermos or something, you can see where it's up to. You can see if it's half full or nearly empty, because you can actually see through the ceramic or whatever it's made out of. And also, if kids were wearing glasses, they looked like sunglasses on camera, because while optic light, the light that we see in the rainbow around us, the glass lets that light through, whereas something like metal blocks it out. For infrared, glass blocks it out, but metal lets it through. So if you actually look on the lens of an infrared camera, it's metal. It looks like it's just not taking anything in, but it's actually the other way around. So then if you're wearing normal see-through glasses on an infrared camera, you look like you're wearing sunglasses because they're just blocked out completely.
Now, infrared is the normal way of seeing direct planet detection. Is that right?
Yeah.
Not that there's a normal method, but
yeah. So, well, infrared detections are very common in astronomy. First of all, because a lot of the interesting chemical signatures that we care about when we look at planets happen in the infrared region. If you're doing things like, if you're looking in the UV and stuff like that, you probably have better luck looking at, young stars. They emit a lot of UV radiation. Or you're talking about things like X-ray, you might be looking at black holes. And I mean, this is just generally speaking, all of these are interesting in all ranges of light. It's always interesting to see in any range. But infrared is very useful for exactly kind of planets and chemistry and stuff like that.
Well, because one of the reasons why I think infrared is good in this particular thing, and correct me if I'm wrong here, is that obviously one of the problems of seeing a planet going around its host star is the host star is incredibly bright. So the planet's just lost in the glare. So if a planet's too close to the star, you're never going to see it because it's just going to be lost in the glare. But if it's a long way out, you're also not going to see it because it's not as though it's reflecting a lot of light off that star because it's so far away now. But it still will be quite warm. It will still be quite hot and therefore giving off infrared radiation. So you can get it out of the glare of the star, but you can still see the heat coming off the planet and actually see it and actually physically see the thing going round the star. So
yeah, that's right.
I mean, that must have been incredibly exciting for when they first started doing that, like actually seeing planets. Yeah.
Oh, don't get me started.
Because there's got to be some advantages, hasn't there, in terms of direct detection?
I mean, if nothing else, the thrill of knowing it is indeed a direct detection. I think that's merit on its own. There's always asterisks on everything that we do. This is why we write long-winded papers on every publication or every piece of research we discover. If our papers that we published were just saying, we found this thing, trust me, that would be pretty short. Yeah. You have to give your introduction and state your methods and your conclusions. And really the reason that it's so important is because we need to let other people scrutinize how we did it, what we're justifying, and what is there that we are claiming as our evidence, because it is so nearly always indirect. If you are seeing A, how do you know that is related to B? So with the direct detection, if you can justify that it is indeed a good direct detection, that's massively exciting.
Yeah, and presumably you can then, once you've discovered that thing, you can keep looking at it and watch it go round, and therefore know about its orbit, know how far out it is, probably work out roughly how big it is because of the type of heat signature it is and things like that, which is loads more than you can do with radial and the radial velocity and the transit. Because transit, you know nothing about its mass, right? You only know about its size, really. Yeah,
this is actually exactly why we launched CHEOPS, the ESA mission, because the idea of CHEOPS is that it is focusing on planets that we have already made mass estimates for using things like the radial velocity from the ground. The CHEOPS telescope was a telescope, it's space-based, that was launched December 2019, I believe. And its task is to measure very, very accurately the radius and the diameter of transiting exoplanets. And a lot of people, when they were, journalists were asking about CHEOPS and stuff, and they're like, oh, you're going to find new planets. No, we are looking at planets we have already detected, and we are looking at how big is it. Because if you have the size and you have the mass, you can work out the density. And that's the exciting one, because that's the one that tells us, is it rocky, is it watery, is it gaseous, and all those exciting sort of chemical, geophysical questions. So there's a lot of merit in all of the things we can gather about a planet, and in any way you do it, because you can also always use them in tandem with other types of observations that build a bigger, better picture. Kind of like how when you are say that you are observing a galactic center far away. If you look in the X-ray and you look in the ultraviolet and you look in the visible and you look in the infrared and you look in the radio, then you can build up a big picture of what's happening, because all of these different things build up to make one big picture. It's all the instruments coming together to play the orchestra. And in the same way, using different methods, using different techniques with exoplanets are building a bigger, better picture that paints this and this story about what a wonderfully diverse set of planets we have in our universe.
Oh my God! I mean, when it comes to because we've got such a small collection of planets in our own solar system, yet they're all so ludicrously different.
Honestly, like, we're the ragtag team of the universe.
Well,
we're just.
But it makes you think. Well,
it's the Breakfast Club.
Well, but it's like we can't just be lucky and have like a diverse set of planets. You think to yourself, well, if we've got this diverse set of planets, then surely there's just so many variations on the planet. Yeah. I mean, it'd be really annoying if somehow we've managed to have all the variations on planets. But let's face it, even Pluto was a massive surprise when they went past it with New Horizons. It was like, we weren't expecting it to be that exciting.
And I mean, we've already started looking at a, let's say, sufficiently large sample size of other solar systems to know that there is diversity. We're probably a little bit more exotic than we thought, but that could also have to do with bias in our detection methods. Like all of the detections that we've discussed here, nearly all of them favor detecting larger planets first because they're just easier to spot. You know, it's easier to find the big old tree.
Well, especially with direct detection, presumably it's almost impossible to see rocky planets using direct detection.
Yeah. So nearly all of these methods favor that. So when we say like, oh, we're finding a lot of large planets, that could also be a reflection on how we're doing it. But I mean, there's so many planets, and just from the little bit of surface that we've skimmed so far, we've already found so much diversity. And one of the most common questions, I think, when people ask about exoplanets, so often it's of course asking, do you think there's life in the universe? And my answer is always an overwhelmingly positive yes. And I'm saying that, you know, what we know about the chemistry in the universe, it's not that weird to have chemistry happen. And it's not that weird to have planets around other stars. So with how many stars there are in our universe and what a fraction we've seen so far, absolutely. And then the next question is always something like, oh, so you think we're going to encounter aliens in our lifetime? And I'm like, absolutely no way. Well, I mean, those are two very different questions.
Well, yeah, exactly. I think when people ask the question, is there life, is there going to be life out there in the universe? What they're actually asking, is there going to be intelligent life?
Am I gonna meet the aliens and party with them? And I think the big question, the big thing that people forget, it's just the universe is so bloody big.
Yeah, I mean,
and of course, and people really do picture a lot of the time. I don't blame them, by the way, but people often tend to picture like the aliens swing by for an hour here or there, you know, blow up the White House maybe, and then fly away and high five. And I mean, it's just there. Even if there was some kind of communication brokered, you wouldn't get replies for a really long time. Yeah. So it's just
even if we were to discover a exoplanet and like with the James Webb Telescope go, oh my God, it's actually got organic life on there. We know
they've got a sign up. They're waving.
Yeah, they're waving. It's like it would still be really depressing because there's no way of communicating with it in any reasonable time frame, and certainly no way of getting there.
No. Exactly. Neon sign saying land here, but it was erected 50 million years ago.
Yeah, so tough. I tell you what, shall we listen to my interview with Alok Jha? Then I've got a really exciting one about how exoplanets can be used in other science. They're not just places where there might be life. You can use them for something else. How about that? So here's the interview. Aikute.
The Interplanetary podcast, putting the ace back into space.
So I'm joined on the podcast by Alok Jha, who is the science correspondent for The Economist magazine. Welcome to the podcast.
I'm very pleased to be here. Thanks.
Well, it's an absolute pleasure to have you on. I mean, this came to me because I saw an article of yours in The Economist about exoplanets. So I thought you'd be an excellent guest to just shoot the breeze about exoplanets. Because the article, in fact, you can tell us a little bit about the article, but the sort of main thrust was that we're starting to know more and more about exoplanets, and we might actually start to see some super exciting exoplanets soon. So, yeah.
Yeah, so just to give you a bit of context, I've been reporting astronomy and planetary sciences and everything from black holes to moons of Jupiter and things for a long time now. It's just something I'm interested in, and it's coincided, of course, with an amazing flowering of research into these topics. I mean, we've always, since humans have looked up to the stars, we've been interested in stars and planets of our solar system. But only 30 years ago did we discover the first planet beyond our solar system. And since the first one took many, many years and decades to actually find, but then since then we found thousands. And there have been many missions by NASA and the European Space Agency that have been sent up to look for there are different techniques to look for planets that sort of orbit other stars. And the current estimates are that there could be trillions of exoplanets outside our solar system. And this is incredible. I mean, it's a really exciting, rich seam of astronomy. And sort of on the other side of that, there's this sort of question of, if we're looking for life elsewhere beyond the Earth. I mean, and everyone who's interested in space research kind of secretly deep down is interested in that question, right? I mean, yeah. I am. I'm sure you are as well. And it's kind of, for a long time in the 60s and 70s, 1960s, 1970s, I forget, we've changed centuries now. Anyway, in those times, it was seen as a kind of fringe activity, looking for life. It was little green men. It was like made fun of. And the people who did it were sort of on the fringes of science. But actually, in the last 20 years, the search for life beyond Earth has become very mainstream in science. And I argue in the piece for The Economist that, the search for life is now the most exciting frontier in astronomy. And there are lots of things you have to do to understand how to search for life, including become better biologists. And so biologists have got involved, planetary scientists, geologists, all these people that traditionally have never done any astronomy, but now they are full square in the center of the most exciting bits of astronomy. You need astronomers who can detect photons of light from many light years away and detect the gravitational wobbles of planets and stars. You need a biologist to tell you what kinds of molecules and kind of pictures of life might be existing somewhere else in different planets. You need a geologist to tell you how those planets might have formed in that solar system. I mean, there's so much discovery going on, and it's become this. It's happened in the last few decades, and I think in the 2020s, where we're about to discover some really, really interesting, exciting things that I think questions we've asked for a long time might begin to get answered.
Yeah, do you think that over the course of a lot of interviews like this, that the one thing that seems to come up is the ability to crunch data seems to be the big thing, as in we're collecting more and more and more and more and more data, and it's the ability to sift through that. Would you say that the kind of data sciences element of it is just as important as the instrumentation and, like you said, the biologists and the geologists?
All of it's really important, of course, and data science has been one of those things that's underpinned so much of scientific progress in the last 4 or 5 decades. If you look at the genetics and the genomic sciences, that is essentially, as well as being obviously a biological science, it's about understanding how to collect, sift through, store, share data. And we've been doing genetic sequencing has become cheaper and cheaper and cheaper. You can do an entire genetic sequence of a human now for $1,000. It cost billions 20 years ago to do just one, and took a long time, took years. Now you can do it in less than a day. So as that technology's got better, we've collected more data. But then, of course, once you have all the data, you need a way to make sure that it gives you proper insights. Data is just numbers and fact and everything. You need biologists, you need physicists, you need all these other people to get insights and knowledge from that data. But yeah, astronomy has benefited from that too. More sophisticated instruments have been sent up into space. They're being built on the ground as well, telescopes, even more sophisticated than ever. And all of them are producing incredible amounts of information that can then be processed and stored and shared algorithmically across the world. And do you know what? We're only at the beginning of all that. As I said, the next 10 years, we're going to collect even more data, probably more data. I'm going to get this statistic wrong, but the amount of data that scientists even in astrobiology will collect in the next year is probably more than all the data they've collected so far. So you need good ways of going through all this stuff as well.
Yeah, I mean, I know that Gaia in particular pumps out just tons and tons of data every second, and that those large arrays of telescopes require special hard drives that can cool properly and things like that, because they're collecting so much data.
Well, exactly. And also, it's funny you mentioned this bit of the conversation, because the data we're all used to in our daily lives, having data in the cloud and having lots of data stored about our personal lives and all of that. But scientists have had to really push the boundaries in the last few decades, and just the sheer amounts that you can collect on one hard disk or 1,000 hard disks. I mean, they've had to invent new types of hard disks, new types of sort of networking hard disks together. All of this, of course, by the way, it relates to one of my other interests, which sort of feeds into many of the other sciences, which is the particle physics community. Particle physics community, the fundamental science community over in places like CERN and Fermilab, smashing particles together to understand what the constituent building blocks of the universe are. They're the ones who invented the Webb, first of all, back in the late 80s. The internet already existed, the computers were already connected, but they're the ones who invented a way of sharing information across the web, HTML, which is something that seems so obvious now that we all use all the time. And then they also invented ways of using normal computers to collect the absolutely gargantuan amounts of data coming out of the Large Hadron Collider every single second, and sifting through it to make sure that you can actually find new particles or new rules of physics through all of that. And all of that then filters into the other sciences. So the physicists were the ones who really pushed forward genomic sciences, because they were able to understand all this data and use it. And then, of course, all that filters into the real world. So the fact that we can have data centers all over the world connected together comes from the fact that someone in science had to invent something that's never been invented before.
Yeah, well, as a science communicator, do you think that sometimes that might be a problem when you have science that's based really on these massive, huge data sets of essentially ones and noughts, like the Large Hadron Collider? There isn't a picture of an atom being smashed to pieces. It's really just a stream of data that's being interpreted by someone. And it's the same with exoplanets. It's we're not really seeing a picture of an exoplanet, or very rarely anyway. Does that make your job as a science communicator harder to sell the story almost to the public, that it's less of a picture?
Well, so far you're right. The way we've detected exoplanets, there are several methods, but they include looking for the wobbles of a star. So one way is to sort of look at a star over several years and see if it's wobbling around. And if it's wobbling around, then it means that there's some gravitational impact of something that's orbiting it. And so that can be assumed to be an exoplanet if the numbers work. Another way to look for it is to look at a star and to see how the light from that star dips as planets or other objects go in front of it. Now, technically, these are pictures, because you are seeing something using an instrument. But of course, you can't see them with your naked eye. There are lots of things in the universe that you can't see with your naked eye that we have to draw in normal visible light, essentially, so that we can understand what they are, or even talk about in terms of objects that we understand. So we talk about planets in being Earth-like or Mars-like or Venus-like. And I think that none of that is actually, the thing is that a lot of people, even though the actual, when you get down to the nitty-gritty of the science, yes, it is a stream of ones and zeros or slight finding signal in a messy, noisy data set. That's the scientist's job, to do all of that and clean it all up and find it. And when they say they've discovered a planet, what it really means is that in 3 columns of a spreadsheet, they can see a number going up slightly compared to 3 other columns of a spreadsheet where the star doesn't move as much. That's the discovery of a planet. That's what really it looks like. But, actually, it's really easy to sell that to the public. You just say there's a planet. You know what a planet looks like, and there's a planet going around. I don't need to tell you about the columns of spreadsheets. I mean, we could if you wanted to understand all that. But let's leave that to the heart. That's the scientists. When it comes to astronomy and planets, it's so easy to get people interested. As you know through this podcast, I'm sure that people are fascinated by the questions of life or planets or what worlds look like, and you can just imagine that in your head. And if actually we had images, I think that would be a bit more disappointing, to be honest, because then they're just smudges, aren't they? Do you remember last year? There was the first ever picture of a black hole.
Yeah, I was about to bring that up.
yeah. So I was so excited. I've just loved the concept of black holes, all the cosmological, energy, all of that stuff. And I was very excited about the picture of a black hole. And, we know black holes exist. We know from their gravitational impacts, and Nobel Prizes have been awarded around them, and they're weird objects, very important in the evolution of the galaxy. And, when you saw the first picture of the black hole, which, by the way, had taken 4 years of processing to get, it looked a bit like a smudge of yellow light around a dark object. Now, I totally can appreciate how hard that was to produce, but it kind of ruined slightly the image of a black hole for me. Now, I've got over it, and I think it's amazing, and I love it, and there have been various updates to it. But to me, I don't need a picture of a black hole to imagine and be fascinated by it. I like the fact that they exist now, and obviously they're scientifically very interesting. But I've never had problems imagining all this stuff. And looking forward, however, in the next 20 years, the telescopes that are being built on the ground, so the European Extremely Large Telescope, which will be built by the end of the 2020s, then there's another one, I'm going to embarrassingly forget the name, is an American one, the 30-meter telescope, which is potentially going to be in Hawaii. Telescopes like that, they will actually be able to take physical pictures of exoplanets. You'll be able to see the exoplanets and detect things in those atmospheres. And some of those might be visible pictures. But I don't think any of them will be as amazing as the ones in your head.
Yeah, well, the only reason why I brought it up was precisely because of that black hole picture, because you and I know that picture is absolutely incredible, and the effort that goes into it is just phenomenal. And in actual fact, it does show a black hole for the first time. They don't kind of exist until you have a picture of it, and it is a picture of it, right? So, but it's a bit disappointing compared to the picture that we see in Interstellar or something like that of a black hole.
That's right.
And so you can see why sometimes it's the science communicator's job's made a little bit trickier by the fact that that certain things that are amazing aren't necessarily seen as being as cool and as incredible as they perhaps might be.
That's right. I think a lot of things in astronomy or even fundamental physics are abstract because they're so small or they're so big, or we simply can't send a camera close enough to a black hole to take a close-up picture. And actually, you wouldn't see much anyway in that place. Because our human senses are tuned to a very small set of frequencies of light. And, we're not meant to be able to see all this stuff. But the fact that we can do it through sort of instruments we've invented still has to be translated into something we understand. And a lot of that stuff is abstract and mathematical, and you have to imagine. And human imagination can do a lot of that stuff. And it's okay to do it that way, I think. Maybe one day we'll get an even better picture of black hole. But let's hope so.
Let's go back to life. And like you said, that secretly, really, a lot of stuff that we do in space is to try and see if we're alone in the universe, right? So if we start with somewhere like Mars, because we don't even have to go to exoplanets, do we, before we try and look for life. But if say over the next 10 years or 20 years, we have definitive proof that life started also on Mars, where presumably that affects the research and the money pouring into exoplanets and the excitement around them.
Yeah, I think that would be incredibly exciting if we found that there was evidence of life on Mars. And we've been trying to find that evidence for many decades now. Mars is the most visited planet from our space agencies, but partly because it's the one we can get to most easily. And it's very similar to Earth. It has a very similar history to Earth. 3.5 billion years ago, when life is thought to have started on Earth, Mars and the Earth were very similar planets, similar atmospheres, similar amounts of water on the surface. So obviously one planet went one way and the other has become a sort of desert now. It's fairly well established, I would say, and I don't want to make predictions here, but it's fairly well established that there isn't any life that exists on Mars right now, at least on the surface, because the surface is very highly irradiated. It's very non-friendly to life, and we haven't detected it. But there could be fossils of life. It could be that there has been life in the past. It could be that right now, if you dig under the surface a few meters, where the UV radiation from the sun doesn't penetrate, that you might find some sort of microbes or something. So, people are still looking. And the rovers on Mars now, so there's the Perseverance rover, which landed a few months ago. NASA's Perseverance rover I think is the first scientific experiment on Mars that can actually detect life if it exists right now. So far, everything we've sent can detect elements of what might be life or conditions for life, but not actually life itself. Except if a creepy crawly actually crawled over the lens, camera lens of one of those things, right? But that was the only way those previous missions would have been able to detect life definitively. With Perseverance, it's got experiments that can do much, much more sophisticated analyses of the rocks to look at structures that might be created through lifelike processes. It can do more sophisticated analyses of the chemicals in the soil, et cetera, et cetera. And then it'll be joined in a couple of years by another rover, the Rosalind Franklin rover from the European Space Agency. And this one will be able to drill into the surface, so drill a couple of meters down to see if there's anything down there. These things are sort of part of a longer-term plan by the European Space Agency and NASA to actually bring back samples from Mars. So it's one thing to send a rover and send a whole load of chemistry labs to Mars to do experiments there and send information back. But of course, the chemistry labs on Earth are much more sophisticated and much, much better. And they can detect things in a much more meaningful way. So you want to bring samples back. And so Perseverance will, if it finds something interesting, it will do its own analysis, but then it has a set of titanium tubes on board, which it can, if it finds an interesting sample, it can put something in those tubes, seal it up, and just leave it on the surface. And the idea is that in a few years, another mission will go, land on the surface, near where these tubes have been laid on the surface of Mars, collect them up, and then launch itself off Mars and come back to Earth. It's a joint European Space Agency, NASA mission, the Mars sample return. And it's going to be incredible if it works. The idea then would be that you'd get these tubes of Mars sample back, and then you could put them into your mass spectrometers and other experiments here on Earth and discover the sort of history of the geology of the planet, including whether there's been life there or not.
That is it's a very long process, isn't it? Because you're collecting samples, then sending other missions to collect those samples and bring them back to Earth, and then obviously you've got the analysis. So might we be in a position with these extra large telescopes coming online and more sophisticated spacecraft like James Webb Telescope and stuff like that, might we start seeing evidence for life on exoplanets before we see it in our own solar system?
That's a really good question. The exciting part, I'll answer it in two ways. One is that it's exciting that we can even ask this question.
Yeah.
Isn't it? It's really exciting that the equipment that you might be able to use to detect signs of life far, far away are getting so good that it might produce a result before you get definitive answers of life on Mars. Now, there are things to say about this, which is that maybe there was never any life on Mars, and we've been looking really hard and we've done our best and there's nothing there. And so therefore, the first signs of life we are going to detect, if we detect them, will be somewhere else. So that's just, what's true or not. The thing is that I think that Mars is difficult because the surface has been so irradiated that any signs of organic life or any remnants would have been so smashed to smithereens by the radiation that it's very hard to detect stuff. And, the places we've landed on Mars are the equivalent of the Sahara Desert, because that's where it's easier to land. So imagine if an alien sent missions to Earth and they landed only in the Sahara Desert, you'd think that the rest of the planet's like this. Well, actually, no, there's all sorts of different locales and stuff. I exaggerate slightly. So I think that if there has been life on Mars, then Perseverance and the missions we have there, including, by the way, the Chinese rover, which will land in a few months, they've got a good chance. And if they don't find anything in the next few years, then it's likely that tells me that it's very unlikely life ever existed on Mars. We still have to dig underground, but it tells me that it's not likely to have existed. The more exciting thing, actually, in terms of on the flip side of that, with regards to exoplanets, it's very, very, very hard to get measurements from exoplanets, but we're getting instruments that are going to be really sophisticated and very high definition in the next 10 years. And so what we're going to do is we're going to find that we can measure the amounts of individual molecules of things in nearby exoplanets. We're going to take pictures of them. We're going to look at understand their climate. We're going to do all this stuff. Now, all of that isn't necessarily... all of that is only useful information if you can put it into context. So you need to have a really good theory of what life does to a planet. So therefore, you can really definitively say something is a sign of life, you need to have a theory that tells you, a really well-developed theory that tells you biologically, here's how life might behave, here's the kinds of effects it has on the planet, and then what of those effects can we detect from many light years away. This is a big plank of what's called astrobiology. This idea of how would evolution by natural selection is probably operating all over the universe. So how would different environments create different types of life? What kinds of molecules would they put in the atmosphere? What kind of metabolisms they would have? All of this stuff is theoretically being worked out here on Earth now. On Earth, I say, as if like this being worked out somewhere else. Who knows? So biologists are working on this now. They're doing experiments to look at how different planets might create life differently. And all of that has to be tested. So we can get all these detections from planets outside our solar system, but making meaning out of them is going to be very difficult, and it's going to take a long time. It goes back to the point you made very early on. We're going to have loads of data, tons of data. It's going to be fantastic amounts of data, but finding out knowledge from that data is going to take some time because we're going to go down blind alleys. We're going to think, let me give you an example. 10 years ago, it was thought that one of the surefire ways of finding life on another planet would be if we detected oxygen in the atmosphere. And so that seems sensible because oxygen on Earth is largely produced by life. You don't naturally get lots of oxygen in the atmospheres of planets because it's a very reactive molecule. So it reacts with anything around it. So on Earth, it's produced because of photosynthesis, and that's how you have 20% oxygen in the Earth's atmosphere. So, well, great, good sign of life. So we started looking for oxygen in places. However, biologists came up with another idea, which is that, hang on, if you had lots of ozone in an atmosphere, which is easy to produce, and you had a star that created lots of UV light, it would break up the ozone in the upper atmosphere, and lots of oxygen would produce that way too. So that's a false positive. Now, it doesn't mean that oxygen isn't a sign of life. It just means you have to be really careful when you just use this one measure. If we're going to claim a sign of life somewhere else, we're going to have about 1,000 of these really sure. We have to be certain that this is one piece of it. There's another piece of it. There's another piece of it. We're going to build up a picture, and it's going to take a long time to do that. So I think that actually our solar system is probably going to give us signs of life before. If life exists here, we'll get that before. And the most exciting place to look for that isn't Mars, I think. It's a bit further out in the solar system. It's the moons of Jupiter and Saturn, Enceladus, Titan, Europa. These are, I think, the most exciting places to look for life, where you can actually probably get some sort of mildly definitive answers in the next decade or so. Because if we sent a mission to Europa, Europa is one of the moons of Jupiter. It has a thick, icy crust. Underneath the icy crust is an enormous ocean of liquid water. We only knew it had liquid water in the last few decades. That liquid water sits on minerals, sits on rocks, and is probably quite warm because of the tidal forces acting on it. There's a lot of energy going on there. And so that means that those are the conditions you might create life. Because on Earth, if we look back 3.5 billion years, one of the most promising hypotheses for how life started was that it started at the bottom of the oceans near hydrothermal vents. So you have all this energy, this heat, you have lots and lots of minerals and lots and lots of air, of water moving around. And there you create these metabolic processes or things that became metabolic processes. There are places where chemical reactions can happen that began to create the molecules that you sort of eventually would become life. So that's the theory of how life started on Earth. So if you have the same environmental conditions on Europa or Enceladus, then why not life there too?
Yeah, I mean, unpacking what you've said, there's a few avenues that worry me in terms of astrobiologists only have a sample pool of one to kind of base their extrapolations on, and so so there must be wildly different thoughts in that community in terms of how varied life could be, or no, it really needs to be this specific, and the signs of those various lives and what it might look like. Presumably, the field of astrobiology is, I don't want to say contentious, because presumably there's not enough skin in the game for people to get contentious about it. But presumably there's lots of different ideas and opposing schools in that community.
Well, we should probably say that in this entire discussion we talked about looking for signs of life elsewhere. What we mean by that is looking for signs of life like our life. So like life on Earth. Life on Earth started 3.5 billion years ago. Every single life form on Earth is related to every other single life form back to that point 3.5 billion years ago. So, and it's evolved from very simple organisms to the diversity we see today. Everything from trees to elephants, all came from that single point. And we know that because all life on Earth is based around DNA and proteins and the same chemistry, essentially. And that chemistry is tuned to the conditions of life on Earth. And so when we've looked for life elsewhere, we look for exactly the same thing. And partly that's because that's what we know to look for. The universe of possibilities is infinite, so you have to start somewhere. But that doesn't mean that all of life on Earth in the universe will be like ours. So yeah, you're absolutely right. There are people on the sort of fringes of astrobiology who will argue that when we're looking for life like ours, in other words, looking for oxygen, looking for water, looking for methane. These are the things that life like ours produces and needs. But what if life elsewhere doesn't use any of that stuff? What if it's based on silicon or uses methane as its instead of water, or other complex molecules, and there are chemistries you can theoretically put together that would make for life. They're life like we would never recognize. You and I wouldn't think of this thing as life, but that let's not get into the question of what is life at this point. That's the whole podcast.
But it does make Titan particularly exciting, doesn't
exactly.
it? Because
I was going to come to that. So you could have a different chemistry on Titan because of the chemicals available there. You'd need a molecule. You could sort of abstract what life is. Life like ours uses DNA to store its information. It uses proteins to build itself and communicate and all of that. So all of our hair and hormones and everything, they're all proteins. And DNA codes for those proteins. And it uses water as the medium for everything. So it uses the chemistry of water to move things around and move energy in and out of places and create cells and all these things. There are ways of using other complex molecules to do those three jobs. One is storing information, one is building things, and one is the medium for it all to work in. You could imagine other things, but then it gets really complicated because then we're into the world of theory of what does this life do? Then what are the byproducts of it? So what do we then look for? And you don't know what you're missing in terms of the errors you might be making. But these ideas definitely exist. And the weird thing is, of course, that we might look in lots and lots of places for life, and we might look for decades and find nothing, but we've just not been looking for the right thing. And actually, it's been there under our noses all along, and we'll never find it until we come up with the right theory for it. I don't know. It's a difficult one because at the moment we found no life out elsewhere, so we might as well look for what we can. We have to build our instruments to look for something. Yeah. And you can't build an instrument that looks for everything. Otherwise it's useless. Right?
Yeah.
If you're building a telescope, it's tuned to certain frequencies of light because otherwise you've not got infinite money to build a telescope that does everything. And then also when you get the information from that, how do you interpret it? So scientific experiments have to have a hypothesis. They have to have a specific thing they're testing. If it doesn't work, you build another hypothesis with another instrument. And that's just how science works, unfortunately. You have to go through all the avenues.
Do you think, talking about the looking at exoplanets and using certain instruments to do it, the phosphine in Venus's clouds, I don't want to call it a debacle, but it's quite close to being that. Is that indicative of what might happen soon with exoplanets, where we start looking at exoplanets and people will come up with theories and go, oh my God, this is really exciting. And under closer examination, it might be not as exciting. We're going to start seeing perhaps more stories like the phosphine story in Venus.
Yeah, I think you're definitely going to see more of that because this is such a theoretical enterprise in terms of... So the phosphine story, I wouldn't call it a debacle. It's how science works.
Yeah.
And, what happened there was that over many years, a group of scientists saw an excess of this gas phosphine in the atmosphere of Venus, and they looked for... when you make a detection like that, first of all, you have to make sure it's real. So they found this phosphine. Right, that's one thing. But then what does that mean? Well, they only knew it was interesting because many, many papers have been published about all sorts of organic or non-organic gases in atmospheres and what constitutes a signal of biological activity versus natural activity. So you simulate all sorts of natural chemical reactions that might happen on a planet that you know the composition of, and where you know the atmospheric dynamics, and you put them into a computer model, and you get some results saying that actually for an atmosphere like this, made of these elements, these are the kinds of gases you'd see in these sorts of distributions, and you refine that model, and that itself, those models are entire careers in science and in building those things, right? But then you need to test these things in the real world, and we don't have that much data really of other planets. So people argue about different ways of how different processes that might go on in different atmospheres and so on. And some people say that process A doesn't occur in a planet, and therefore you're going to have a bit more of the gas than you expect. You're getting into the real nitty gritty here. But the point is that all of that then gives you a reference database. And then it allows astronomers to say, right, okay, if we agree that these are the gases we looked for, in these concentrations, then any excess we see must be something interesting. It's not explained in our models. So phosphine was one of those gases which you can't explain naturally on a planet, because on Earth, phosphine only exists in very weird bacteria, very rare bacteria, or in meth labs. So either way, it's biologically produced.
Yeah.
It's not natural in the sort of geological sense. So people got excited about this, and they did a very good job of trying to look for other sources of phosphine and just couldn't. And, the theoretical models said phosphine is an indicator of life. Now, when the university researchers published that research, they made it very clear, look, we don't think this is necessarily a sign of life. We just think this is really interesting. Now, of course, everyone jumped on it, didn't they? Because it's just so interesting. It's like, look, we've been looking at all these planets all over the galaxy. And look, right next to us, Venus, it's there. It's been there all along. These life forms. And, in science fiction, Venus has life forms which float in the clouds and do all sorts of other things. And all these models and ideas exist, and they were unearthed around the time that the phosphine discovery was made. And so what happened is that, of course, when you make a big claim like this, it's checked independently by other scientists. So lots and lots of attention was put on this claim, and several scientific groups couldn't replicate the results. And that's the first step in really having an idea accepted within the scientific establishment, is to repeat the result with an independent analysis. So the different groups couldn't repeat the result. And then they found that there was some a sort of a calibration error in one of the instruments that had been used to gather the data, which the original team had processed to then get the result. Once you corrected that error, and this was no fault of the teams, by the way, these are very sophisticated instruments, that take a lot of calibration and operation. Once you corrected for that error, then the significance of the discovery of phosphine was reduced. Now, they still discovered it they still think it's there, but they're not as confident as they were before. And so, that's where it's at the moment. Now, this tells you something, which is that if we can't work out what's on our next door planet using instruments that we can really train there, and we can send probes to Venus, and we have done. There are some on the way. And if we can't work out what's on Venus, can you imagine how difficult it's going to be on planets that are tens of light years away? And yes, to answer your initial question, we're going to see loads of this stuff. We're going to loads of people arguing about whether they've seen signs of life or not. Because think about the stakes. Whoever does find incontrovertible evidence of life, whether it's a molecule or something else on a planet thousands of light years away, that person goes down in the history books forever as the person who led us towards discovering life elsewhere. A question that every one of us as humans has asked. And we're at the stage where we can start to answer it. Of course, it's going to be competitive. Loads of people will argue and shoot each other down. But I'm afraid this is how science works. You come up with an idea and everyone else will pick holes in it, and it looks a bit messy. I'm all for it. I'm all for scientists arguing in the public. I think it's good. As long as everyone's transparent and working for the best interests of the science and not being personal or vicious, I think it's completely okay. And this is why I think I'm hesitant to use the word debacle, because I think that the scientists who made the initial discovery of phosphine did the best work they could, and they've done great work in being transparent about their results afterwards and accepting criticisms. And the scientists who criticized them have also been very honorable in the way they've acted. So let's not say that it's been a bad thing. I think they'll just continue discovering what's going on there.
Yeah, I mean, I definitely don't think it's a bad thing, because presumably we've learned loads more about detection. No, I've got one. Let's wrap this up with one question in terms of, say there is an exoplanet and we have a slam dunk detection of life that after everyone's gone over it with a fine tooth comb, it's a slam dunk. It's like, yes, we found life on this exoplanet, and it's one of the nearby ones. It's it's in TRAPPIST or something. One of the
Proxima Centauri. That's 4 light years away.
Okay. Let's say it's Proxima Centauri. Say like it's a slam dunk life detection of Proxima Centauri. Then what? Because I often think of this as a bit like you're desperate for some ice cream. you phone up and you find a place that sells ice cream, but it's too far away that you can never get the ice cream before you get there and it's melted.
I mean, I think you've hit the nail on the head. I think I don't think that there's a clearer or more beautiful way of describing it than the melted ice cream analogy. I really don't. I think that's brilliant. I'm going to nick it for future articles because it's brilliant. But you're absolutely right. Once you've discovered life elsewhere, let's assume that it's been proven to be true. What do? If it's microbes, they can't communicate with you. You might think that, the thing about light speed is that it does travel at a certain speed. And if something's 4 light years away, if there was technological life on that planet, you might be able to communicate with it, but with a 4-year delay. I mean, that's something. But if it's microbes, you're not going to communicate at all. You'll be excited. And I do wonder what will happen, because people will get excited and then they're like, oh, well, that's it then, I suppose. That was it. Well, there is life elsewhere. We're not alone in the universe. Scientists will be fascinated, obviously, because it tells us about the universe and how what other life forms might exist and all of that. But I don't know. It's going to be a bit deflating after a while.
Well, it doesn't really answer a question, because there's that Arthur C. Clarke brilliant quote about, if we're alone in the universe, that's terrifying. But if there's life else out in the universe, it's equally terrifying, right? They're both amazing. They're both like the yes or no answer is both incredible. So we should kind of continually be in a state of, oh, that's incredible. But if we answer the question, we're still no further to sort of being anywhere almost.
This is so here's how I look at it. I think that the current state of science might lead you to a point of, oh, that's a bit of a shame. I'm never going to have the ice cream. I'm never going to be able to interact with it. And then you sort of go off with the rest of your life doing whatever you want to do. But just think, a few decades ago, we didn't even know that exoplanets existed. 60 or 70 years ago, we'd never even been into space. I mean, we're so early in the exploration of space. Really, really are scientific exploration. We can look the other end of the universe now with our telescopes and detect photons from the Big Bang and all of that sort of stuff. We've been able to detect gravitational waves just only recently. That's within a few decades of starting this work, right? Give it 300 years, 400 years, 500 years. Where is physics going to be at that point? Right now, we can't travel to these places. We can't really communicate with these places. And the laws of physics tell us that we can't. But I don't know what humans will be able to do in 500 years' time. I just can't imagine the rate of discovery, the rate of progress, that something will be able to be done with the knowledge of of aliens. Maybe not in our lifetimes, but 500 years from now, I mean, the idea of traveling elsewhere through some newly discovered law of physics, come on, why not? That keeps me optimistic.
Yeah, I mean, but you're right. It kind of almost is. We would have to discover new physics to get to even Proxima Centauri.
Yeah, absolutely.
Because the distances are so ridiculous. And we're discovering new physics
all the time. I mean, there's muons that are wobbling in a weird way that the experiments in America have confirmed now. That shows us that the standard model of particle physics is not quite right. I mean, we don't know what we don't know.
Yeah, no, absolutely. I suppose it's a bit like if someone 500 years ago got out a telescope and saw life on the moon and thought, well, how on earth do we get there?
Yeah.
Yeah, it's just a similar sort of thing. Literally no idea of how to get there. And I guess us sitting 500 years away from an interstellar human race, if it's possible.
We're only 70 years into the space age. 70.
Yeah.
500 years into the space age. Given we're 70 years into the space age, and in the last 20 years, we've made as much progress as we did in the 40 years before. Do you know? So that exponential growth just will keep going.
Yeah.
I mean, humans are capable of amazing things. We all know that, and we're not even in the foothills of astronomy as far as I can see.
What are you working on next? What's your next few projects?
Well, if you can ever get me out of the coverage of coronavirus, which is sort of taking up all my time now, and what I'm interested in is in terms of astronomy and those sorts of topics is I'm kind of interested in the dark universe. You know, what is it? We don't know what 95% of the universe is made of. This is dark matter and dark energy. Those are just labels for our ignorance, essentially. You know, this is what 95% of the mass energy of the universe is. So there are new experiments going up looking at ways to try and answer those questions of what that stuff is, how we're going to discover it, what that means for the evolution of our universe. The experiments looking at how the Big Bang itself, sort of created the universe. These are all important. Dark matter, dark energy, all this stuff is really important in understanding all of that. And I think it would be really, what I'm really interested in doing is trying to sort of get a hold on where we're at with understanding that. When we talk about exoplanets and discovering life and all this, again, we're talking about life like ours, but not only life like ours, but matter like ours, you know, and most of the universe is nothing like us, or made of the same stuff as us.
Yeah.
And I think that, you know, you suddenly realize you're in this tiny speck in a sea of difference. And I think that I'd like to explore that a little bit more as well.
Yeah, well, no, absolutely. I've every time I see a story about something tantalizing, I saw one the other day about how dark matter itself might have a sort of weird type of magnetism that explains dark energy.
Could be possible.
And it's like, oh my God. And it said, yeah, you don't even need dark energy anymore. It's like, oh my God. Okay. So yeah, and I wonder how much falls out, because there's always a connection, isn't there, between the ridiculous particle physics and cosmology as well. You know, the stuff that happens in black holes, the very large things, is also influenced by the things that are happening in the standard model. And I think,
well, it's all. I mean, everything has to be quantum at some level.
Yeah,
because, you know, just because things are enormous and the galaxy sized, ultimately it's all comes down to how the atoms and constituents of those atoms are behaving in large groups. And, you know, there's so much more to know about how. I mean, obviously we know about gravitation and how it shapes the universe, but how gravitation works at the level of atoms it's a mystery. I mean, I'd say it's a mystery not in the sense that we don't know. It's completely unknown, but we don't have a good model to fit it into the standard model of particle physics. We don't have a quantum description of gravity, which is one of the big fundamental problems in physics right now. And black holes are where you discover, where you're going to find out the answers to these things, because that's where gravitation and quantum physics come together. So yeah, pictures of black holes, gravitational waves, all these things are going to tell us insights into those sorts of big sort of unification type problems. And yeah, you're right. Particle physics seems like a thing you do in big particle colliders on Earth, but actually the fundamental physics going on there determines what happens at the larger scales in some senses. Yeah.
Well, even, you know, it'd be nice just to have something like the rate of the expansion of the universe finally nailed.
Funny nailed, yeah. Like, well, it's, you know, who knows if it's changing as well. That's the other thing.
Yeah, I know. And then you think, oh, it's so complicated. But that's analogous, isn't it, really, to exobiology and all those. There's so many moving parts that it's very, very hard to kind of nail it down. But
the universe is complex.
Yeah, it's almost as if
I think
it's
that's
really
what we're saying, isn't
it? Yeah. Well, thank you very much for giving us the rundown on exoplanets and a lot more. If you've got a hero from the past who you would bring back and say, hey, look what we're achieving right now. Have you got like a sort of superhero?
Well, this is a bit cheesy, but genuinely, in the last few years, a lot of what Albert Einstein predicted in his general theory of relativity has been shown to be true. Now, general relativity has always been, there's been no doubt that it's true, but gravitational waves took a century to detect. He was that far ahead of his time. It'd be wonderful to show him, oh yeah, you were right. Now he probably would have said, yeah, of course I'm right, or something like that. But on a more sort of intrigued level, I'd be really intrigued to know what Charles Darwin thinks of modern genetics, because he obviously, with natural selection, gave that subject of biology of a real it transformed it into a science like no other, and it's led to the genetics and molecular biology we have today. I'd just love to see his mind computing what he created many, many centuries later. It'd be fascinating. And I genuinely think he would be interested and more humble than probably Einstein.
Yeah, I mean, to show Darwin the mechanism of DNA would be just
right,
be
exactly.
incredible, wouldn't it?
Wouldn't
I mean, it'd be
wouldn't
like,
it be amazing?
wow. Yeah,
because he didn't know what the mechanism was.
Yeah, absolutely. Well, thanks very much.
You're very welcome, Matthew.
The Interplanetary podcast is alive!
I came to Alok Jha by a couple of his articles that he's written. They're really, really cool, so you should definitely check them out. Now, I wanted to talk about this thing that was a paper that came out very, very recently, I think this week, published April the 22nd, in the journal Physical Review Letters, and it's by Yuri Shmurnov, vodka-y type name.
Sounds delicious.
Yeah. And he's a fellow at the Ohio State University Center for Cosmology, and Rebecca Linn, a postdoctoral researcher at the SLAC National Accelerator Laboratory at Stanford. And their paper is about how you can use exoplanets, get this, to detect dark matter.
What?
I know. How weird is that?
Get out.
So this is, after reading the abstract, this is what I can just about make out. So you'll have to bear with me. But it kind of makes sense. So planets, right, are huge. They're big celestial objects. So they have a lot of gravity. And we know that the one thing that dark matter does do is interact gravitationally, even though it doesn't seem to interact in any other way.
That's the best hunch we have.
Yeah, so we think
We
that
don't
that's
know
the
a
way.
lot,
We don't know a lot about dark matter, hence the fact that it's dark, in fact. So
That's true. That's something not everyone knows.
Yeah,
it's not just not reflecting light. It's just dark, as in the Dark Ages.
as in, we have no idea what it is, but
just really depressing.
we do know that it reacts to gravity. So if there's large planets around, what will happen is that dark matter should be attracted to that planet and eventually work its way down into the core of that planet, as in it will be basically dragged down. It won't interact with the rock or anything, so it'll just be dragged down to the core. And as it drags down to the core, it should sort of fuse or annihilate with itself and create heat as it does so, right? And maybe if you've got a good enough detector, you can actually spot that heat signature as the dark matter annihilates itself in the core of these enormous planets.
Out the box.
Yeah, so that's pretty cool, isn't it? Now here's the really cool thing, is the fact that the reason why they're excited about it is because obviously there's 4,300 already confirmed exoplanets, but there's just about to be almost another 5,700 added to that list. So there's going to be 10,000 experiments out, 10,000 instruments essentially out in the known universe that we can look at for these kind of experiments.
And the planets start coming, they don't stop coming.
No,
as Smash Mouth once said.
so yeah, absolutely. So it's only booming as a field. So we're only going to have more and more of these instruments. So if you can use them in this way, then this could be really exciting. Now, they're better than neutron stars, because with things like neutron stars, for example, they will soak up dark matter like nobody's business.
Yeah.
But of course,
greedy things.
They are very greedy. But of course, they're massively, chaotic and radioactive themselves. So like splitting out this tiny heat signature from them would be pretty much impossible.
Yeah.
But for large kind of Jupiter-like planets or super Jupiters and brown dwarfs, they're going to be going around soaking up dark matter, and you might be able to spot the heat signature from those sort of cooler planets, because it'll be slightly more than they should be giving off from their normal way that they work. Maybe even Jupiter itself is giving off this small dark matter heat.
Really?
So But obviously, you've got to extract the noise away, and it's going to be incredibly difficult to do. But here's the thing that they think is, as you get towards galactic cores, the dark matter gets denser. So if you start looking at exoplanets that are nearer the core, if they've got more of this heat signature than the planets on the outer edge, you've essentially detected dark matter. You've kind of almost proved that it's there. That's the mouse droppings for dark matter right there. Right?
As you were talking, I was just thinking about how insane it would be to extract such a small signal. But it does help when you have a lot of data points, because what you can then see is, if you can assume that the noise is relatively constant, then it is easier to see changes in, because even if the noise kind of smears the certainty of the signal, you can still see more global trends, like an increase or a decrease, with a lot of data points like that. It wouldn't really be a statistics proof, but it would certainly be very interesting.
Well, yeah, I mean, it's
even just hypothetically, it's a fun thought.
It's a really fun thought, and here's the really cool thing: what really powerful infrared telescope is being launched this year that would have the capability potentially to measure this?
Starts with a J. I love that James Webb is becoming like some kind of weird dump for astronomers, which is like, James Webb will do it. Don't worry about it. They can end any paper like, yeah, this is going to be fine because James Webb will do it.
James Webb will be able to do it. Yeah,
he's going to sort everything out.
It's so late now. Presumably, there's this enormous waiting list for all the experiments that everyone wants to do with it. Mind you, this this one would presumably go quite high up the list if it's going to actually be something where you could potentially massively put some constraints around dark matter and what it is. I mean, that'd be insane, wouldn't it?
That would be insane. And I mean, if there's genuinely good reason for it, then if they can have a good proposal for it, absolutely. They actually have picked out the first cycle of proposals for James Webb. So they have already picked out the experiments, I guess. I don't know what you would call it for it's not an experiment, but the first the first targets for James Webb. It's if anyone's interested, like, do look up the list, because it's really cool to see what a huge range of things that it's going to be doing, and also just all these cool things that people have thought of. Like, it's so great to see how people have been cleverly thinking about how to maximize the use of James Webb in many ways. So I'm excited. I'm very excited.
I'm super excited, but
until it blows up.
Until it blows up. Well, no, Ariane 5, super safe. Yeah. It'll be fine.
Ariane is our goddess. She will take us.
But however, the unfurling of all the stuff that has to happen. That's genuinely
terrifying. Yeah.
I think it's because of Hubble not being quite right when Hubble was launched.
Right.
That must be terrifying for everyone.
We've been spurned before, and we're not ready to trust again.
No. Right. We've come to the end of another exoplanet edition. Thanks very much for joining me again, Linn. It's always
Thank you very much for having me.
Awesome to have you here. And
I'm glad to be back again. I fool me once kind of thing, fool me twice, and here I still am.
I've managed to fool you 3 times now. This is brilliant. But if anyone spotted that I was feeling a little bit Matt sounded a little bit groggy today, it's because I had my AstraZeneca jab yesterday. So yes. So you
can see through time. You can smell the 5G.
Yeah, I can do everything now. I've become superhuman. As Trump said, I'm feeling very powerful. Very powerful. So
oh God, that's creepily good. You've had your first AstraZeneca. You're on your 3rd Moderna, 6th Pfizer dose. You're going to collect them all.
I'm going to collect them all until I become superhuman. Until I find the vaccine that gives me Marvel superpowers.
Yeah, exactly. And then you're going to throw James Webb into orbit.
Oh my God.
Don't need any of these silly launches.
Presumably, if anything goes wrong with it, I can just fly up and fix it.
Yeah. just poke it out a bit.
I could really do with a
God,
superhero.
get some doses. Yeah. I wish I could have some doses. I don't think I'm going to be vaccinated until at least the summer.
Yeah, you're too young and healthy, like you said.
I'm too young and healthy. Maybe I don't know. Is there a way for me to very quickly gain up to, I don't know, BMI of 40? I think that's...
I mean, I could suggest you could like contract some serious illness which puts you on the extremely vulnerable list. But I guess that's not what you wanted to hear. I guess
I'll just wait. Ugh. No, I mean, shout out to all the people I know who have had an incredibly terrifying year with their pre-existing conditions. Full sympathy, and I'm very happy to wait for my dose. I've been very fortunate to basically just shut myself in my apartment cave and do science for a year, so it's kind of been nice.
Yeah, well,
I've been okay with this pandemic. I'd give it a 6 out of 10.
I'm well, the pandemic definitely gets a 1 out of 10 for me. But I'm going to massive shout out to Bob, who's one of our Patreons, who's also works for the NHS vaccinating people, and he's an absolute legend. And
thanks for being a legend, Bob.
I feel as though my vaccination was something to do with Bob somewhere.
Oh, absolutely. Yeah.
So massive shout out to the NHS. I love you.
I love you from afar.
Yeah. Well, you know, we can't all be lucky and have the NHS. I know that there are loads of people going, the NHS is terrible, but it's not. Honestly, I got my jab. So yeah, brilliant.
I lived in the UK for 5 years. I loved every second of the NHS. I only had good experiences, actually.
Yeah, well, it is genius. I definitely can't ever complain about it. Right, that's it. So if you want to see some notes from today's episode, they'll be on www.interplanetary.org.uk. I tell you what would be awesome if you leave a review on iTunes or wherever you can leave reviews, because that really helps to kind of push the podcast. And I have to say there have been some brilliant reviews, and thanks very much for everyone who's done it in the past. But if you get a second, leave a review. And if you really love it, you can join all of us on the Discord and go to and become a patron at www.patreon.com/interplanetary, or just go to the website and follow it through there.
That sounds great. Everyone should do that.
You should absolutely do it.
That's my firm voice, by the way. I know it. I'm not very good at it because I'm smiling.
I thought it was your sort of
please try.
Like your Darren Brown voice, where you kind of persuade people using some.
Do it now.
Yeah, I'll put some sort of backward masking in. And what was that? Do it.
Hello, this is Batman.
Subscribe to the podcast.
This is your subconscious. Please
subscribe to the podcast.
This is ASMR.
And remember, I could have direct detection of you subscribing to.
Yay!
Or
Don't make this an indirect.
Yeah, I can infer that people are listening to the podcast.
Yeah.
By podcast stats, but I can do a direct detection of you if you go on Patreon. It's brilliant.
Yeah.
Or even or even share the odd tweet.
Yeah, leave a review and send us observational data of 5 stars, and we will be very grateful.
Ah, yes. 5 stars. 5 stars. There must be
out of 5, by the way, in case there's 10.
Yes, 5 stars out of 5. Right, that's it. I'm going to go, and thanks very much, Linn. You're always a legend.
Thanks very much for having me.
I can't wait for the next time. We'll have to come up with a super exciting subject.
More exoplanets.
More exoplanets.
I don't know. That's all I love. I just want to talk about exoplanets.
Tough. No, we're doing something else.
Yeah.
We'll
something else. We'll think about it.
We'll get something else. Right. That's it. Bye, Spudcats.